in Calculus 2, and this has to do with improper integrals. An improper integral is something you haven't seen yet. You could have infinity as the limit on the integral, or you could have a domain problem, like, if you're looking at the integral of 1 over x, but you're going from -1 to 1, you know that it's undefined at 0, so how do you handle that? And what is kind of interesting in this section is you start to discover that a curve, if you think of it as the area under a curve, we can actually find curves that have what would appear to be an infinite area. They continue on and on, but they actually have a finite area when you integrate them, because you think of them as limits and you get an actual value for the answer. And so when that happens, we say that the integral converges to a certain number. If the integral doesn't converge, when you take a limit and you get infinity, we say that it diverges. And so we'll have quite a bit of practice, kind of a neat section, because you're going to get to review some of your integration techniques for your test coming up, and then also reviewing some limit ideas as well. All right, so we will go ahead and start. I just took these out of the textbook, and I do encourage you. I almost toyed with just going over the examples that were in the book because they're really good, but then I thought, no, I didn't want to shortchange you. So what I encourage you to do after this is go back and look at the examples. He does a nice job with them. I am going to do one of them because it's so important, but I picked some different examples from the assignments to work. Okay, so you have two types that we're going to consider. One is integrals with infinite limits of integration, okay? And so these are improper integrals of type 1. So you're going to have some integral, and it's going to be from a to infinity. And so what you do when you're thinking about a problem like that is you just assign a finite number b, and then you look at the limit as b goes to infinity. So you go ahead and work the integral like that it's finite, and then you consider the limit at the end. Okay, and then that would be the same for the negative infinity one, or similar idea, except that you go from a to b and you look at the limit as a approaches negative infinity after you evaluate the integral. If you have from negative infinity to positive infinity, then what you're going to want to do is split it up, and it doesn't really matter where, and then split it up like this, and then think of this part as number 2, and then this part as number 1. So in each case, if the limit is finite, if you get a number at the end, we say that the integral converges. And if the limit is the value, and the limit is the value of the improper integral, if the limit fails to exist, then we say that it diverges. And this is going to be kind of a key concept in the next chapter that we study. When we look at series, we often consider whether series converge or diverge. All right, so I want to do a problem before I go through here. So let me have some space here to work a problem. All right, so let's consider the integral from 0 to infinity of dx over x squared plus 1. All right, and so what you do in order to handle this is you think of this as the limit as b goes to infinity of the integral from 0 to b dx over x squared plus 1. And so you're probably going to want to have, this is going to be, as I said, a nice review for integration. You're going to need to think about what this integral is. Anybody got this one? X squared plus 1 in the denominator. What's that integral? It's kind of one that comes up enough that it's worth remembering. Which one is it? Nothing? It's inverse tangent. That's your arc tangent. When it's just that one squared when it's u squared plus a squared, basically. And it's inverse tangent u over a. And I think there's a coefficient in front. You could look at the sheet. But this one, because it's just 1, you're good. So this is going to be equal to the limit as b goes to infinity of inverse tangent x evaluated from 0 to b. And so you'll think of the limit as b goes to infinity of the inverse tangent of b minus the inverse tangent of 0. Okay, and so this takes a little thinking about the inverse tangent. Does anybody, I don't know how much you remember the inverse tangent graph looks like this. It's sandwiched in between negative pi over 2 and pi over 2, and it's just like a little s like that. That's the graph of y equals inverse tan of x. So as x goes to infinity, or in this case, as b goes to infinity, our y value is going to go to pi over 2. So this is pi over 2, and then the inverse tangent of 0, of course, is 0. So your answer to this one is pi over 2. So we say that this integral converges, and it converges to pi over 2. Okay? Let's do another one that's kind of fun. That's example 1. Here's example 2. Let's consider the integral from 2 to infinity of 2 dv over v squared minus v. Okay, so on this one, you're going to want to look at the limit, excuse me, I'm going to sneeze, I think, as, sorry, yuck, I'm sure that sounded wonderful on the microphone, b to infinity from 2 to b of 2 dv over v squared minus v. Okay, so when you look at this one, it's not going to integrate with anything on the table, but it should kind of, I mean, do we have anybody want to, is it leading to you to any of your techniques that you've thought of? Well, this denominator, 2 over v squared minus v, when you see that, you probably should think about partial fraction decomposition, because you can factor a v out, and you can think of that as v times v minus 1. Does that make sense? And so then you can think of that as a over v plus b over v minus 1. And then we'll go through and just remind you how to do this. So you're going to say 2 is equal to, you get a common denominator there, that's going to be a times v minus 1 plus b times v. So 2 is equal to a plus b onto v minus just a. Everybody okay? All right, and so then you should be able to see that your a, negative a, is equal to 2, so that means that a is equal to negative 2, and b, let's see, is equal to positive 2. Because a plus b has to equal 0, right? Because there are no v's over here. And then 2 equals negative a, because those are your constants. So a equals negative 2, which means that b has to equal positive 2. And so that means that you can write this as the limit as b goes to infinity from 2 to b. I'm going to bring this 2 in front. I'll put that 2 right there. And it's going to be 2, well, it's kind of your choice. This is negative 2 over v plus 2 over v minus 1. Actually, sorry. If I put the 2 in front, then that'll make this negative 1 and this 1. Okay, I can do it. This is negative 1 and this is 1, because that's the 2 from there. Okay, so I factored the 2 out. All right, and so then, what is the antiderivative of ln, I just told you, 1 over v, that's ln, right? But it's going to be negative. I'll take a swig of coffee. See if I can pull myself together here. All right, 2, this is going to be negative ln v plus the ln of v minus 1 between 2 and b. All right, and when you're looking at this, the limit as b goes to infinity, This is, you want to think of this as 2. I would use the quotient rule here because really this is ln v minus 1 minus ln v. So you can think of this as ln v minus 1 over v. Are y'all okay? Okay, from 2 to b. So the limit as b goes to infinity of 2 times ln b minus 1 over b minus the ln of 2 minus 1 over 2. Okay, and then as b goes to infinity, where is the ln of b minus 1 over b going to go? Yeah, because it's kind of like, it's almost going to 1. It's like infinity, b over b, right, which is going to be 1, and the ln of 1 is 0. So this is 2 times 0 minus, this is going to be the ln of 1/2. And so you have negative 2 ln 1/2. But can y'all clean that up at all, you think? The negative ln 1/2 is ln 1 minus ln 2, right? So, and the ln 1 is 0. So this is actually 2 ln 2. Are y'all feeling that? Yes? Are you okay? Which you could write as what? If you're feeling really crazy. Yeah, ln 4. Just for fun. Okay. I want that to go away. Okay. I'll come back to the pen. All right, let's see. Let's do, that's probably good. Let me see. Let's do one that's kind of split up. So here's another example. I didn't give myself nearly enough room. Here's another one. We're going to look at the integral from negative infinity to positive infinity of 2x dx over x squared plus 1 squared. All right. Well, when you look at this one, what you want to do is you want to think about the limit. You want to split it up some way. So you might want to think of it. You could split it. I mean, the easiest place to split it up feels like maybe at 0, right? So we could look at the integral from negative infinity to 0 of 2x over x squared plus 1 squared plus the integral from 0 to infinity of 2x over x squared plus 1 squared. All right, this is a pretty quick little u sub. So in order to get rid of the infinity, you're going to look at the limit as a approaches negative infinity from a to 0. So if u equals x squared plus 1, du is going to equal just 2x. And so that's going to be du over u squared. And then this one, we'll think of it as the limit as b goes to infinity, the integral from 0 to infinity, and this will be du over u squared also. Okay, and when we evaluate this one, that's u to the negative 2. So we add 1 to the exponent, which is negative 1, and put it over it. So it's negative u to the negative 1, but u was 2x. So negative 2x to the negative 1 between a and 0, plus the limit as b goes to infinity of negative 2x to the negative 1 between 0 and b. I forgot to put a b right here. So this is the limit as a goes to negative infinity. This is going to be this is going to be trouble, isn't it? Yeah, but when I plug 0 in, it's going to be undefined. This is going to be infinite. Okay, so this is going to be, yeah, you can write it as negative 1 over 2x minus, or so this will be plus 2 over, plus 1 over 2a. And when I plug 0 in here, I get yucky. And then the same problem here. I'll get negative 1 over 2x, or 2b, minus, so it'll be plus 1 over 2x. And I wonder if we can...
It's a break in the line.
Pardon?
It's a break in the graph.
I guess I should have thought of this one before I started to work it. Smooth. Hold on. Yeah. Wow. Okay. Well, that's good modeling. It turns out that it doesn't matter where you split it up. So maybe you should split it up where it's not going to give you any trouble. For example, instead of splitting it up it gave us trouble when we split it up. So if you want, you can split it up somewhere else. Let's split it up at 1. Okay? Since it doesn't matter, you can change this to 1. All right? And then when you plug 1 in, you're going to get negative 1/2. What are you going to get as
your conference is scheduled to end in 2 minutes.
Of 1 over 2a. Yeah, this is going to go to 0. And then this is also going to go to 0 as b goes to infinity. So you're going to have negative wait a second. I'm losing my mind here on my notation. So since I went to 1, then the x I can take out, and I'll just put a 2 here. And then this was 2b, and then I'll put a 2 here. Okay, so this one goes to 0, this one goes to 0. Then you have negative 1/2 and positive 1/2, which cancels out. So this one converges to 0. Sorry. Okay. All right. Now, this is kind of a really important concept, this next one, and it's actually in your textbook, but I wanted to go over it with you because we're going to use it a lot in the next section when we talk about P-series and tests for convergence of series. This is a really popular P-series question. Okay. So what we want to do is we want to say, okay, well, what if you have an integral that looks like this? From 1 to infinity of dx over x to the p, right? When will that converge, and when will it diverge? And if it converges, can we figure out what the value is?
Your conference is now over. Goodbye.
And so what we want to do then is begin by assuming that P is not 1. Because when P is 1, you get ln x, and so that integral is kind of different, but let's just consider all the values when, either positive or negative values of P. So let's consider when P is not equal to 1, okay? So what we would do is we would look at the integral from 1 to b of dx over x to the p. And so what would that, how would that integrate? How do you handle that? What is the antiderivative? As long as it's not 1, what is it? Well, you can sort of think of it as x to the negative p dx, right? And so then what do you do to that? When you, like if it were x squared, what do you do? If it were x so if it were, you add 1 to the exponent and put it over it, right? So if it was negative 2 or negative 3, it would be 1 over negative 3 plus 1, so negative 1/2, right? I can't even, just say it was x to the negative 3 dx. What's the antiderivative of that? Well, you'd add 1 to the exponent, so it would be x to the negative 3 plus 1 over negative 3 plus 1, right? And if it were any of them, that's what you do, right? And sometimes it flips over, but whatever, you don't worry about it. So in general, if it's going to be negative p, it's just going to be x to the negative p plus 1 over negative p plus 1. Do y'all agree with that? Yes, okay. And so if you wanted, you could look at this integral. You're going to evaluate it from 1 to b, and you're going to think of the limit as b goes to infinity. All right. So we have, let's see if we can write this a little bit nicer. I could think of this as 1 over negative p plus 1. Maybe I should write that as 1 minus p. Okay, that's just a constant that's out in front. And then it's going to be b to the negative p plus 1, b to the negative p plus 1. And then minus 1 to the negative p plus 1. Okay, and we need to think about what's going to happen as b goes to infinity. As b goes to infinity, it's going to depend on what the value of p is, right? So what is, if p, can you give me any kind of thoughts on what would be true? Like if p were less than 1, what would happen? If p were less than 1, this would make this positive, right? And so as b goes to infinity, this would go to infinity, right? Okay. What if p were greater than 1? What if p were greater than 1? Like say p were 7, what would happen? This part would definitely go to 0, wouldn't it? If p were 7, then this would be b to the negative 6, 1 over b to the 6th, as b went to infinity, that part would go to 0, right? This part, where would this go? Well, if p were 7, this would be still just 1 over 1, right? So then this, it's almost like it doesn't matter. We don't need this because it's 1 to any power is still 1. So we almost don't even need that. We know this is just going to be minus 1. Okay, so when p is greater than 1, we will get 1 over 1 minus p times negative 1, right? Which when p is greater than 1. But when p is less than 1, what do we get? We get that it goes to infinity because this whole thing is going to grow without bounds. So it's going to go to infinity. All right, so it might be better to write this as because you're multiplying by negative 1, it's kind of messy. Another way to write this would be just to flip this, you know, like factor a negative 1 out of this. So this will be negative 1 plus p, and then the negatives would cancel, you know, if you factor a negative 1 out of this. And so you could write this as p minus 1 and then just ditch that negative. Does that make sense? So you could write this as 1 over p minus 1 when p is greater than 1, or infinity when p is less than 1. Is that okay? All right. So what about if p is equal to 1? Well, if p is equal to 1, then you're just going to look at the integral from 1 to infinity of dx over x, which is going to be the limit as b goes to infinity of the integral from 1 to b of dx over x, which is just the limit as b goes to infinity of the ln of b minus the ln of 1. Well, what is that limit? It's infinity, right? Which means that this integral diverges. Okay? And then this also means that it diverges when p is less than 1. Okay. So in general, we can say that the integral from 1 to infinity of dx over x to the p diverges when p is greater than, or sorry, less than or equal to 1 and equals 1 over p minus 1 when p is greater than 1. Okay, so later on in the next section, you're going to be looking at these series 1 over x squared, the series of 1 over x squared, and you're going to learn that that actually converges, whereas the series 1 over x diverges. And you use the integral test to show that. You use this little idea that we just looked at to show it. So kind of keep this one in the back burner as one that is kind of interesting. It depends on the value of this exponent to whether it's going to converge or diverge. Okay. All right, so The next type of integral that you can have, of improper integral that you can have, is integrals of functions that become infinite at a point when the interval of integration are within the integral of integration. And these are called improper integrals of type 2. So it could be that it's discontinuous at one of the endpoints, or it's discontinuous somewhere within the interval from A to B. And so what you do is you just look at the limit, as you approach either from the left or the right, that particular problem area. And in each case, we still say that if we say the improper integral converges, and that the limit of the value of the improper integral, and the limit is the value of the improper integral if it exists, if it's finite, and if it does not exist, then we say that the integral diverges. So let's look at an example. This one page is really, I don't know, it took it a long time. Okay, so I think we're on about example 4, or maybe 5. Yeah. Let's look at the integral from 0 to 4 of dx over the square root of 4 minus x. So when you look at this one, you're probably saying to yourself, well, it doesn't have an infinite limit, but it does actually have a problem because it's not defined at 4. The domain of the function, it does not include 4, because if you put 4 in there, you're going to get 0 in the denominator, right? And so, and actually, it can't be any bigger than 4, because if you put 5 in there, that would make it a negative. Okay, so what you want to do is look at the limit as some value approaches 4. So we could say the limit as b approaches 4 from the left. We're going to come up to 4 from the left because that's where it's defined. All right, and so we'll write this as the integral from 0 to b. And then we can write that as 4 minus x to the negative 1/2 dx. And you can do a little u sub on this one. If you let u equal 4 minus x, then du is just going to be negative x dx. So you're just going to have a negative, just negative dx. So you'll just have a negative in front. Okay? And so u to the negative 1/2 is going to be what? What's the antiderivative of u to the negative 1/2? U to the negative 1/2. Antiderivative of u to the negative 1/2. I know. Do you remember how to do this? This is Cal 1. What is it? That helps, Ms. Brooks. Now I just feel bad. Yeah, add 1 to the exponent, put it over it. So 2u to the 1/2. You with me? Yeah, I know. You're trying to do something fancy, and it's just not. Okay. So what we'll say here is our u was 4 minus x to the positive 1/2, and we have a negative from the u substitution. All right, and we're going to evaluate that between 0 and b. So we're going to look at the limit as b approaches 4 from the left of negative 2 times 4 minus 4 to the 1/2, b to the 1/2 power. And then we're going to subtract, we'll put a 0 in there. So negative 2 times 4 minus 0 to the 1/2 power. Okay, well, as b approaches 4 from the left, this is going to go to 0, right? And then if you plug, or if you solve this, you'll just get the square root of 4, which is 2, times negative 2, which is negative 4, and it's a minus that. So that's just going to be 4. All right? So that was a fun one. Okay, let me look at another one. I think I might have one more planned. Here's another example. Okay, example 6, what I want to do is look at the integral from -8 to 1 of dx over x to the 1/3 power. So what do you notice about this one? What are you thinking when you look at this one? Are you thinking anything? Well, hopefully you're thinking that this function is not defined over the interval from -8 to 1. There is a problem at 0, right? So you need to split this up. You need to think of it as the integral from -8 to 0. Plus the integral from 0 to 1. And then what you'll do is you'll look at the limit as b approaches 0 from the left of this integral from -8 to b of, we can write that as x to the -1/3 dx, plus the limit, and you could say as a approaches 0 from the right, the integral from 0 to 1, let me start a to 1, of x to the -1/3 dx. Okay, and so this is the limit as b approaches 0 from the left. You add 1 to the exponent, which will make it 2/3, and put it over. It's just going to be 3/2 x to the 2/3, evaluated between -8 and b, plus the limit as a approaches 0 from the right of 3/2 x to the 2/3 between 0 and 1. Or a and 1. Okay, and so then this is the limit as b approaches 0 from the left of 3/2 onto b to the 2/3 minus -8 to the 2/3. And then on this one, it's going to be the limit as a approaches 0 from the right. You can factor that 3/2 out. You're going to have 1 to the 2/3 minus a to the 2/3. Okay, now as you go to 0 from the left, this is going to go to 0. And 8 to the 2/3 power, the cube root of 8 is 2, but then cubed is 8. So -2, because this is the cube root of -8 is -2, but squared is +4. So this is going to be 3/2 times -4 plus, here you're just going to get 3/2, because that's going to go to 0. And so your answer is going to be, do you agree? Yeah. Did you come with the answer? Or nothing? I get no noise. Okay, so this is -6 plus 3/2. So is that like -9/2 or something? Because it's -12/2. Yeah. So -4.5. Okay? All right. So you can see they're kind of tedious, and I remember when I was working these, when I first learned how to do these, or when I was first exposed, I'm not sure I learned the first time I looked at them, I remember thinking, oh my gosh, I already hate integrating, and now I have to do limits, which I never really felt that great about either. And I haven't done one yet. We probably will with L'Hopital's rule, but it can be thrown in there every now and then too. But we like L'Hopital's rule. Like if you get infinity over, that's where you get to take your derivatives. But the limits that we've done so far have been real easy. They've either been 0 or infinity, but you may have a little bit trickier limit in your problems. I don't know. And some of the examples in the text, they had more interesting limits. Okay, he did give you a little sort of, in the book, he gave a little, some examples of the two types of limits, and I wanted to look at these because they're kind of cool for what you can think about. I'm going to just give you the answers to these and not work them. They're in the book if you want to look through the work, but it's kind of fun because, you don't necessarily you may not think that it diverges or converges, and it's just kind of an interesting problem. So let's see. We'll look at the first one, that ln x over x squared. It turns out that if you go through the work on it, you actually do have to do L'Hopital's rule and do some work on this one. This is in your book, page 604. But it turns out that this integral is equal to 1. And so what's interesting is that this area under this curve, although it appears to be infinite, it's actually finite. It has a finite value. All right. The other one I really like in the book is this one, where number 3, where they go from negative infinity to positive infinity. This one ends up having this area right here is pi. So, it's just weird. To see a picture of a shaded area picture of pi, a graphical picture of pi. To me, I think that's kind of strange. It turns out that this one, from negative infinity to 0, this is pi. This is obviously pi over 2. That one's pi. So you can go through and do these if you want. So all 3 of these examples that he did actually converge to finite values. Okay, I can't remember whether he did these other ones. I don't know whether he did these ones in the text. Yeah. The integral from 0 to 3, let's see. Yeah, he does this one. The integral from 0 to 3, it turns out, does actually converge to 3 plus 3 on the cube root of 2. So, and again, it's strange because it goes, you know that it's going to have this sort of infinite behavior. It has an asymptote at 1, but it kind of continues on. But what happens is, I guess that space gets small enough, fast enough, that it does actually converge to a real number. So everything starts to get really mysterious because, what we're saying, even just with what we just looked at, which was this P series, this will freak you out, maybe. And I have trouble sleeping at night when I think about this. Back to this one, this integral from 1 to infinity of dx over x to the p. If you just look at the integral from 1 to infinity of dx over x, right? Graphically, maybe I'll come over here and look at it on the nursery paper. Graphically, what that means Well, all that's saying is, okay, 1 over x, and this is from 1 to infinity, 1 over x is this curve right here, right? And so here you are at 1, and then you're going to infinity, right? And so that graph, I wonder why it won't let me pick a color. We're just looking at all of this area right in here, right? And they're telling you that that area is infinite. It diverges, right? I can't tell you what that area is because as it goes to infinity, it keeps getting more and more, right? But if I were to look at the integral from 1 to infinity of, and we said when p was greater than 1, we would get a value. So if I were going to look at the integral from 1 to infinity of, say, 1 over x squared, well, what does that graph look like? Pretty much the same thing. It just gets smaller a little bit faster. But that area is actually finite. This freaks me out, right? So this one is divergent, but this one is convergent. You can actually get this answer to be, it's 1 over p minus 1. So this answer is 1. The integral from 1 to infinity of 1 over x squared is 1, but this diverges. It seems so strange that they're so similar, and yet one converges and one diverges. And so what happens in chapter 11 is we look at this thing called a series. We'll say, put a k here. And we'll say k goes from 1 to infinity. And all that means is you increment k. So this is going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus, you continue that, right, to infinity. Keep adding smaller and smaller values. We will prove that this diverges. It never gets close enough. Even though you're adding a number closer and closer to 0, it never hones in on a number. But this one, which is 1 plus a 4th plus a 9th plus a 16th plus a 25th, right? That one actually converges. And it took Euler like 73 years to prove that it converged to pi squared over 6. It's extra information. But anyway, it's to me, what? What? Where did pi squared over 6 come from? What are you talking about? I just think that's creepy and weird. What's the difference between this problem, this series, and these integrals? Well, the only difference is that a series, it doesn't have the stuff in between. Like between 1 and 1/4, you don't have any number. You're not going to do all the numbers between 1 and 1/4, whereas this one is continuous. So this is it's like discrete. You see what I'm saying? It's just adding certain points, whereas this is adding all the points in between. So you can actually say what it converges to. It's just wild. Don't you think that's wild? I don't know. It still bothers me. Okay. So the last thing in this section is looking at whether a integral either converges or diverges, and we have a couple of tests that we can use to help us. And what you want to do is, if you have a complicated integral, you can just try and integrate it just directly and decide whether it converges or diverges. It converges if you get a number, it diverges if you don't. But if you can't evaluate it directly, then you can try to compare it to an integral that you know does converge, and then if you know that one converges, then you can, if the one that you have created, or the one that you're thinking about, you know it converges, if your function is always less than it, then it would have to also converge, because obviously if one that's bigger than it converges, then one that's even smaller would have to converge. But if your series is f of x, and you know that it diverges, and the one that you're looking at is always bigger than one that you know diverges, then you have to know that this one diverges as well. Okay, so it's kind of like on this, well, if you know that 1 over x diverges, or say 1 over x squared converges, 1 over x cubed, which will always be smaller than 1 over x squared from 1 to infinity, it must also converge. And then in the same sense, x to the negative 1 diverges, x to the negative 2, which will always be bigger from 1 to infinity, must also diverge. So that is the direct comparison test. So let's do an example of the direct comparison test. I always found these a bit challenging because I never knew like what to compare it to, or I was like, well, I don't know. And I think you kind of just get to where you sort of have a sense of what would be a good one after you work enough of these. Okay, so let's look at a problem like this integral from 0 to pi of the sine of theta d theta over the square root of pi minus theta. Okay? Well, if this one has some, you have to kind of do quite a bit of thinking on this problem, but in the end, what we want to do is we want to compare this to the function 1 over the square root of x. We want it because if we could compare it to 1 over square root of x between 0 and pi, we know that that function converges, and we could probably say that this function between 0 and pi is going to be less than 1 over the square root of x. Why can we say that? Well, what can y'all say about the sign between 0 and pi? The sign is going to have a value between, the most it will ever be is 1, right? It'll be between 0 and 1, the sign value. So the sign of theta will be between 0 and 1 on the interval from 0 to pi. So if you just didn't worry about this and thought of it as 1 over the square root of this pi minus theta, and then were to think about, you could prove that this function converged, then you would be able to say that this function also converges, because having that sign in the function is only going to make it smaller, equal to or smaller, because the most it'll be is 1, but it could be 0, which would make it, it could be like a half, or, square root of 3 over 2, or, whatever, but that would still make it less than. So if we can prove that 1 over square root of pi minus theta converges, then we can prove that the sine theta over 1 over square root of pi minus theta converges. So let's consider the integral from 0 to pi of 1 over the square root of pi minus theta, d theta. All right. Well, if we do a u substitution here, we can let u equal pi minus theta, then du is going to equal negative d theta, right? And now we are going to have trouble at pi because we're going to have to look at the limit as b goes to infinity of the integral from 0 to, as b goes to pi, coming in from the left, of the integral from 0 to b, and then this will be, we can think of this as negative u to the negative 1/2 du. And so this is the limit as b goes to pi from the left, and you add 1 to the exponent and put it over it. So this is negative 2 u to the, well, what was u? U was pi minus theta to the 1/2 power, and we're going to evaluate that between 0 and b. All right, and then the limit as b goes to pi from the left of negative 2, I'll put the negative 2 in front. So this is going to be pi minus b minus square root, and then minus the square root of just pi. Okay, now as b approaches pi, you're going to get pi minus pi, which is just 0, so this is going to go to 0, and then this limit is just going to be 2 on the square root of pi. Okay, so this converges. Now, on the interval, from 0 to pi, the sine of theta over the square root of pi minus theta will always be less than or equal to 1 over the square root of pi minus theta. Do we agree? Why? Right, because on that interval, and actually in general, the sine goes from negative 1 to 1. Its range is from negative 1 to 1. So the sine will never be, all that it'll do is make that smaller or the same, okay? And since this integral, 1 over the square root of pi minus theta, converges, we can say by the direct comparison test that the integral from 0 to pi of sine theta over square root of pi minus theta d theta also converges. Okay? So it takes, what you always seem to kind of wonder, well, what function am I going to use to compare it to? But again, that one sort of should have felt kind of like a good one to use. Okay, there's another comparison test, or another test called the limit comparison test. And I will show you that one now. Let's look at the limit comparison test. It says, if the positive functions f and g are continuous on an interval from a to infinity, closed on the a, and if you look at the limit as x goes to infinity of f of x over g of x, and you get a constant, some number L, then we can say that either both of those integrals converge or both diverge. So if you can find an integral that either converges or diverges and then do a limit comparison to the integral that you're unsure of and you get a finite value, then you can say that that one also must converge or diverge. Okay? So let's look at a problem. So here's an example. Say we want to consider the integral from 0 to 1 of dt over t minus the sine of t. And we want to determine whether it converges or diverges on the interval from 0 to 1. Okay, well, if you let f of t equal this function, which is 1 over t minus the sine of t, and then we'll come up with another function. Our other function is going to be g of t, we're going to call it 1 over, and we'll say 1 over t cubed. And it's like, why did you choose that? And I think as an example, if you just go with me on this, and then you'll kind of start to see a pattern to why you chose it, why we chose that one. So we're going to let g of t equal 1 over t cubed. And then what we want to do is look at the limit well, in this case, I guess when you look at this problem, you're probably saying to yourself, Ms. Brooks, there's no infinity. Why? How am I even going to know to use the limit comparison test? But there's a problem on this problem, isn't there? I mean, when you look at this integral, do you see that there's trouble? Where's the trouble at this integral? Yeah, it's 0. And so we can actually, instead of at infinities like these are doing, you can actually put it in at the spot where you have trouble. So we can look at the limit as t goes to 0 and make the same sort of argument. So let's look at the limit as t goes to 0 of f of t over g of t. And see if we can get that to be a finite value. So this is going to be 1 over t minus the sine of t over 1 over t cubed. So that's the limit as t goes to 0. You can flip that, and it's going to be t cubed over t minus the sine of t. And you should kind of convince yourself this is going to be 0 over 0. So we can use L'Hopital's rule. And we'll have to do it several times. This is going to be 3t squared over, this will be 1, and then the derivative of the sine is cosine. So this is going to be minus cosine of t, and that's still 0 over 0. So we'll do it again. The limit as t goes to 0, this is going to be 6t over 1 plus the sine of t, which is going to be 0 over 1, or 0. So, did I mess up?
Is that 1 supposed to be the 1 plus sine t?
Oh, no, it should be. Yeah, plus sine t. So that's still 0 over 0, which is yucky. So we'll use L'Hopital's rule again. And we'll get 6 over negative, or no, just plain old cosine t, which now, okay, and then we get 6. Okay, so our limit is 6. So that tells us that if we can show that what happens to 1 over t cubed on the interval from 0 to 1, if we can show that it converges or diverges, then we'll be able to say what happens to dt over t minus the sine of t. So you can kind of see that we chose the 1 over t cubed because we got to do this. It was a fun L'Hopital's. It was an easy limit to evaluate, right? So let's see if we can figure out what happens on the interval from 0 to 1 of 1 over t cubed dt. One over t cubed dt. Well, obviously you have a problem at 0, so you need to look at the limit as b approaches 0, or you could say a. They seem to choose a. As a approaches 0 from the right, of the integral from a to 1, t to the negative 3 dt. All right, so this will be the limit as a approaches 0 from the right. You add 1 to the exponent, put it over it, so it's negative 2t to the negative 2, evaluated from a to 1. All right, so this will be the limit as a approaches 0 from the right of, now when I plug 1 in, it's going to be negative 2 times 1 to the negative 2 minus negative 2 times a to the negative 2. Well, yeah.
Sorry, maybe I'm screwing up. On the limit, the negative 2, t to negative 2, shouldn't it be t negative 2 divided by negative 2?
I was like making up. Yeah. Add 1 to the exponent, put it over it. I have no excuse. Except I'm tired. Are y'all tired? I'm not feeling it. All right. Now, yes, thank you for helping me. Okay. Back to this. Anybody have a thought besides that? So this is just the limit as a goes to 0 from the right. This will be negative 1/2. And then this will be plus 1 over 2a squared. As you approach 0 from the right, what kind of numbers approach 0 from the right? Well, from the right. Yeah, but they're like fractions, like a half, a third, a fourth, a tenth, a thousandth, 100,000th, right? You know what I'm saying? Like, so really small numbers coming in from the right. So where is this thing going? Where's 1 over 2a squared going? It's going to infinity. So that means that this is an infinite, which implies that it diverges. Right? So if it diverges, we can say that the integral that we just used, and we were given the integral from 0 to 1 dt over t minus sine t, will also diverge by the limit comparison test. Okay? Yeah, and I mean, the thing is, and this will be where you'll I really encourage you on the homework to look at the show me an example. There's nothing wrong with that. Look at the examples in the book, really process them. Also remember I posted all of the solutions to Chapter 8 homework. I mean, did you see that, the textbook solution? So if you're just a total go-getter, this section, the textbook has like 64 opportunities for success in this stuff, and it would be a really good review of integration techniques, and you have the answers there, so you could look at, the more examples you look at these, the better you get, especially with this idea of the the comparison test, because it's just like, it seems like you're just pulling out of the air the function that you're going to use. Like, why did I pick 1 over t cubed? Well, I picked it because it looks very nice. I mean, and the limit when I divide them is very nice. But, I only know that because I have some experience doing that, and I've seen examples before. It's not because I'm like a genius. All right, so have fun with this section, and that will be it. We'll take our tests over this chapter. All right.